Niels Bohr's early life and inspiration were crucial in shaping his path to becoming one of the most revolutionary scientists in history. Born on the 7th of October 1885 in Copenhagen, Denmark, Bohr's childhood was steeped in intellectual curiosity, which was nurtured by his family's academic and scholarly environment. His father, Christian Bohr, was a respected physiologist, and his mother, Ellen Bohr, came from a well-educated family. This combination of scientific and intellectual influence provided a fertile ground for Niels Bohr's early fascination with the mysteries of nature and the physical world. From a young age, Bohr showed a keen interest in scientific subjects, particularly physics. He enrolled at the University of Copenhagen in 1903, where he studied under the tutelage of some of Denmark's most prominent scholars. It was during this time that Bohr's passion for physics truly began to take shape. His focus was on understanding the fundamental principles of mechanics, electromagnetism, and the emerging field of quantum theory. These early academic pursuits helped Bohr lay the groundwork for his later discoveries, which would redefine atomic theory and quantum mechanics. While at the University of Copenhagen, Bohr was particularly influenced by the work of German physicists such as Max Planck and Albert Einstein. Planck's work on the quantum theory of radiation was groundbreaking, and it offered a new way of understanding the interactions between matter and energy. This idea of quantization, which had first been introduced by Planck, fascinated Bohr and would play a pivotal role in his future theories. Albert Einstein's work on the photoelectric effect, which demonstrated the particle-like nature of light, also had a profound impact on Bohr's thinking. Einstein's work suggested that light, once thought to behave solely as a wave, could also act as a particle under certain conditions. This concept of duality, that light could exhibit both wave and particle characteristics, resonated deeply with Bohr and would form the basis of many of his later ideas. Bohr's time in Copenhagen was marked by his burgeoning intellectual development, but it was his time in England, particularly at the University of Manchester, that would catalyze the breakthrough that would make him famous. In 1911, Bohr traveled to Manchester to work with Ernest Rutherford, a physicist whose research on atomic structure would revolutionize the way scientists thought about the atom. Rutherford's experiments had shown that atoms had a small, dense nucleus at their center, surrounded by a cloud of electrons. This discovery shattered the long-standing model of the atom, which had been based on classical physics and assumed that atoms were indivisible particles. Bohr was deeply inspired by Rutherford's work and sought to build upon it. Bohr's breakthrough came in 1913, when he introduced his own model of the atom, which would forever change the course of atomic theory. In Bohr's model, the atom consisted of a central nucleus, made up of protons and neutrons, surrounded by electrons that orbited the nucleus in fixed, quantized orbits. This idea of quantized orbits was revolutionary, as it went against the classical understanding of electrons as being able to occupy any position around the nucleus. Bohr's model explained the stability of atoms, which classical physics had been unable to do, and also accounted for the observed emission spectra of hydrogen. In essence, Bohr showed that the energy levels of electrons in an atom were quantized, meaning that electrons could only exist in certain discrete energy states. This insight laid the foundation for what would later become known as quantum mechanics. While Bohr's model was groundbreaking, it was not without its challenges. The concept of quantization was difficult for many of Bohr's contemporaries to accept, as it went against the principles of classical physics that had been the cornerstone of scientific understanding for centuries. However, Bohr's brilliance lay in his ability to reconcile these new ideas with existing knowledge. His model of the atom was not only mathematically elegant but also experimentally supported, as it successfully explained the spectral lines of hydrogen and the behavior of other atoms. This success propelled Bohr into the scientific limelight and solidified his reputation as one of the leading figures in the emerging field of quantum theory. In addition to his work on atomic structure, Bohr's early life and inspiration were also shaped by his personal experiences and interactions with other scientists. Bohr was known for his humility and his ability to collaborate with other scientists. He was a natural mentor, and many young physicists who would go on to make significant contributions to quantum mechanics passed through his Institute for Theoretical Physics in Copenhagen. Bohr's willingness to engage in intellectual debates and discussions with his colleagues was key to the development of his ideas. He was not only focused on his own research, but also on creating an environment where others could thrive and contribute to the collective understanding of the physical world. One of the most notable aspects of Bohr's early life was his commitment to the idea that science was a collaborative endeavor. While many of his contemporaries were solitary figures, Bohr valued the exchange of ideas and believed that scientific progress was best achieved through open dialogue and collaboration. This philosophy was reflected in his establishment of the Institute for Theoretical Physics in Copenhagen in 1921. The institute became a hub for physicists from around the world, and it played a pivotal role in the development of quantum mechanics. Bohr's ability to bring together diverse perspectives and foster a collaborative atmosphere helped to create a vibrant intellectual community that produced some of the most important discoveries in modern physics. Bohr's early work was also influenced by his deep philosophical reflections on the nature of science and reality. He was deeply interested in the philosophical implications of quantum theory and its potential to challenge traditional views of the world. His work on complementarity, which argued that objects could possess seemingly contradictory properties depending on the type of experiment conducted, was a direct reflection of his philosophical thinking. Bohr was not content with simply developing mathematical models or theories. He sought to understand the deeper implications of his work and to explore how his discoveries fit into the broader philosophical context of reality. This willingness to engage with the philosophical dimensions of science set Bohr apart from many of his peers and allowed him to see the world in ways that no one else could. Through these influences and experiences, Niels Bohr's early life laid the foundation for his later contributions to physics. His ability to synthesize ideas from diverse fields, collaborate with fellow scientists, and engage in philosophical reflection allowed him to see what others could not. His vision would go on to transform our understanding of the atom, light, and the very nature of reality itself. Niels Bohr's intellectual journey, inspired by the work of his mentors and shaped by his own curiosity, would lead to one of the most significant scientific revolutions in history. In conclusion, Niels Bohr's early life and inspiration were defined by his relentless curiosity, his willingness to challenge existing ideas, and his commitment to scientific collaboration. These qualities allowed him to see the atomic world in a way that no one else could, laying the groundwork for some of the most important developments in modern physics. His work continues to influence the field of quantum mechanics and atomic theory to this day, and his legacy as a visionary scientist is firmly cemented in the annals of history. Niels Bohr's revolutionary work in atomic theory and quantum mechanics was not only a product of his intellectual genius, but also a result of his ability to challenge existing paradigms and to think outside the established frameworks of classical physics. Building upon his early experiences and the inspiration he gained from other pioneering scientists, Bohr's contributions would redefine our understanding of the atomic world and pave the way for the development of modern quantum mechanics. One of Bohr's most significant breakthroughs was the introduction of his model of the atom in 1913. This model represented a radical departure from the classical understanding of the atom, which had been influenced by the earlier work of J.J. Thomson and Ernest Rutherford. Rutherford's model had suggested that atoms consisted of a dense, positively charged nucleus surrounded by negatively charged electrons. However, this model could not explain the stability of atoms or the observed emission spectra of elements, especially hydrogen. Bohr's insight was to propose that electrons in an atom occupied fixed, quantized orbits around the nucleus, and that they could only exist in specific energy levels. Electrons would absorb or emit energy when transitioning between these energy levels, a concept that helped explain the discrete lines observed in the hydrogen atom's spectrum. This revolutionary concept of quantization was inspired by the work of Max Planck, who had introduced the idea of quantized energy in 1900 while studying blackbody radiation. Planck's work suggested that energy was not continuous but instead existed in discrete units or quanta. Bohr extended this idea to the atom, proposing that electrons could only occupy specific energy states, much like the energy levels of a musical scale. The quantization of these orbits was a bold and innovative concept that fundamentally challenged classical physics, which had always viewed orbits as continuous and variable. Bohr's model, however, successfully explained the spectral lines of hydrogen and offered a much-needed solution to the problem of atomic stability, a dilemma that had baffled physicists for years. Although Bohr's atomic model was a remarkable achievement, it was also met with skepticism from some physicists. The idea of quantized orbits seemed counterintuitive, and many in the scientific community were reluctant to embrace such a radical departure from classical mechanics. Nevertheless, Bohr's model was supported by experimental evidence and soon became widely accepted. The Bohr model was instrumental in the development of quantum theory and provided a crucial stepping stone for future discoveries. However, it was not without its limitations. For instance, Bohr's model could not explain the behavior of atoms with more than one electron or the fine details of the spectral lines of hydrogen. These limitations were addressed later by more advanced quantum models, such as the Schrödinger equation and the Heisenberg uncertainty principle. As Bohr continued to refine his ideas and develop his theories, he became increasingly involved in the broader philosophical and conceptual implications of quantum mechanics. One of his most profound contributions was the principle of complementarity, which he introduced in the mid-1920s. This principle stated that objects could exhibit seemingly contradictory properties depending on the type of experiment or observation performed. For example, light could behave as both a wave and a particle, depending on the experimental conditions. Similarly, the behavior of subatomic particles could be understood in different ways depending on the context of the measurement. The principle of complementarity was one of the most significant philosophical contributions to quantum mechanics. It challenged the classical view of nature, which assumed that objects could be described in terms of definite, independent properties. Instead, Bohr argued that the properties of quantum systems were context-dependent and could not be fully understood without considering the observer's role in the measurement process. This idea was a direct challenge to classical determinism and paved the way for a new way of thinking about the nature of reality. Bohr's views on complementarity were further developed through his work on the Copenhagen interpretation of quantum mechanics, which he developed in collaboration with Werner Heisenberg and other physicists in the 1922. The Copenhagen interpretation proposed that the wave function, a mathematical description of a quantum system, did not represent the physical state of the system itself, but rather the probability of observing different outcomes. According to this interpretation, particles did not have definite properties until they were measured, and the act of measurement played a crucial role in determining the outcome of an experiment. This was a radical departure from classical physics, which had always assumed that objects had definite properties independent of observation. The Copenhagen interpretation was not universally accepted, and it sparked intense debates within the scientific community, particularly between Bohr and Albert Einstein. Einstein famously rejected the idea that quantum mechanics was inherently probabilistic, arguing that God does not play dice with the universe. Bohr, however, defended the probabilistic nature of quantum mechanics, maintaining that the uncertainty inherent in quantum systems was not a result of incomplete knowledge, but was a fundamental aspect of nature itself. The debates between Bohr and Einstein were some of the most famous intellectual exchanges in the history of science. While Einstein's view ultimately did not prevail, the debates highlighted the deep philosophical and conceptual challenges posed by quantum mechanics. In addition to his theoretical contributions, Bohr played a key role in shaping the future of quantum mechanics through his work as a mentor and leader. In 1921, Bohr established the Institute for Theoretical Physics in Copenhagen, which became one of the most important centers for research in quantum mechanics. The institute attracted leading physicists from around the world, including Werner Heisenberg, Wolfgang Pauli, and Max Born. Bohr's ability to foster collaboration and encourage the exchange of ideas was instrumental in the development of quantum mechanics and the growth of the scientific community. His institute became a hub for the development of new ideas and theories, and it played a central role in shaping the course of modern physics. Bohr's influence extended far beyond his own work. He was a passionate advocate for the peaceful use of atomic energy and played an important role in the development of nuclear physics. During World War II, Bohr fled Denmark to escape the Nazi occupation, and he eventually made his way to the United States, where he contributed to the Manhattan Project, the U.S. effort to develop an atomic bomb. Despite his involvement in the project, Bohr was deeply concerned about the implications of nuclear weapons and spent much of his later life advocating for international cooperation and the peaceful use of nuclear technology. Niels Bohr's legacy is immense. His contributions to atomic theory, quantum mechanics, and the philosophy of science have had a profound and lasting impact on the development of modern physics. His ability to challenge established ideas, his willingness to embrace uncertainty, and his commitment to collaboration and intellectual exchange set him apart as one of the most important figures in the history of science. Bohr's work has shaped not only the field of physics but also the way we understand the nature of reality itself. His vision of a quantum universe, where uncertainty and complementarity play a central role, continues to influence scientists today and has paved the way for future discoveries in the world of quantum mechanics and beyond. In conclusion, Niels Bohr's groundbreaking contributions to atomic theory, quantum mechanics, and the philosophy of science have had a profound and lasting impact on our understanding of the universe. His work on the Bohr model of the atom, the principle of complementarity, and the Copenhagen interpretation of quantum mechanics revolutionized physics and paved the way for the development of modern quantum theory. Bohr's ability to challenge existing ideas, his commitment to collaboration, and his philosophical reflections on the nature of reality have made him one of the most influential figures in the history of science. His legacy continues to shape our understanding of the quantum world and inspires new generations of physicists to explore the mysteries of the universe. The Bohr-Einstein debates stand as one of the most intellectually intense and philosophically significant exchanges in the history of science. At the heart of their debates was the question of whether the universe, at its most fundamental level, operates according to deterministic laws, or whether there is an inherent probabilistic nature to reality. This was not just a matter of technical disagreement, but a clash of deeply held worldviews that shaped the course of modern physics. To understand the profound impact of their debates, it is essential to examine the views of both Niels Bohr and Albert Einstein on quantum mechanics and how their philosophical outlooks influenced their scientific perspectives. Bohr, as the champion of quantum mechanics, argued that the universe was fundamentally indeterministic. The early 20th century had witnessed the rise of quantum theory, which was built upon the groundbreaking discoveries of Max Planck and Albert Einstein. These ideas suggested that energy, matter, and even light were quantized, existing in discrete units rather than being continuous. Building on these concepts, Bohr introduced his complementarity principle, which argued that objects could exhibit seemingly contradictory properties depending on the type of observation made. For instance, light could behave as both a particle and a wave, depending on whether the experiment was set up to observe its wave-like properties or its particle-like properties. This complementarity principle formed a key part of the Copenhagen interpretation of quantum mechanics, which Bohr developed alongside Werner Heisenberg. According to this interpretation, quantum systems did not have definite states until they were measured. The measurement process, in essence, collapsed the wave function into a specific state. Therefore, the future state of a quantum system could not be predicted with certainty, but only with probabilities. The idea that outcomes could only be described probabilistically was revolutionary, as it rejected classical physics determinism, where every future event was seen as a direct consequence of past events. Bohr believed that this probabilistic nature was not due to incomplete knowledge, but was intrinsic to the behavior of subatomic particles. It was a fundamental feature of reality itself, meaning that the universe at the quantum level did not follow classical ideas of cause and effect. Einstein, on the other hand, famously resisted the implications of this probabilistic worldview. He had spent years developing the theory of relativity, which had reshaped our understanding of space, time, and gravity. For Einstein, the idea that nature could be governed by chance or probability was deeply unsettling. He was committed to the belief that the universe was inherently deterministic, that it operated according to precise, predictable laws. Einstein's philosophical stance was shaped by his belief in a rational, orderly universe, one in which everything followed a clear and unambiguous cause and effect relationship. Einstein's resistance to quantum mechanics came to a head in his famous phrase, "God does not play dice with the universe," which he first uttered in a letter to Max Born in 1926. This remark encapsulated his belief that quantum mechanics, with its reliance on probabilities, was incomplete. Einstein believed that there must be hidden variables, unknown factors, that could explain the apparent randomness observed in quantum systems. To him, the indeterminism of quantum mechanics was simply a reflection of our ignorance, a temporary gap in our understanding of nature. He argued that a deeper, underlying theory would eventually emerge, one that would restore determinism to the laws of physics. The debates between Bohr and Einstein became a focal point for the growing divide between two visions of the universe. At the heart of their disagreement was the interpretation of quantum mechanics. Bohr, ever the advocate of the Copenhagen interpretation, held that quantum mechanics was complete in its description of the microscopic world. He maintained that the probabilistic nature of quantum mechanics was not a flaw but an essential feature of reality. According to Bohr, the act of observation was not just a passive recording of events but a fundamental part of the process that defined the state of a quantum system. This view, which emphasized the role of the observer, had far-reaching implications for how we understood the nature of reality. It implied that reality was not a fixed, objective entity, but one that was shaped by the very act of measurement. Einstein, on the other hand, never accepted this view. He remained convinced that quantum mechanics was an incomplete theory. His desire for a deterministic universe led him to propose what became known as the EPR paradox, named after Einstein, Podolsky, and Rosen, in which he challenged the idea that quantum mechanics could provide a complete description of physical reality. The EPR paradox was based on the idea of spooky action at a distance, or what we now call quantum entanglement. In this thought experiment, Einstein suggested that two particles could be entangled in such a way that the state of one particle would instantly determine the state of the other, no matter how far apart they were. For Einstein, this was a clear indication that quantum mechanics was incomplete, as it implied that information could travel faster than the speed of light, violating the principles of relativity. The Bohr-Einstein debates were not simply technical disagreements about the nature of quantum mechanics. They were also philosophical confrontations that questioned the very foundations of reality itself. Bohr argued that the probabilistic nature of quantum mechanics was not a deficiency but a fundamental feature of the universe. For him, the uncertainty and indeterminacy at the heart of quantum theory were not things to be feared but embraced as part of the nature of existence. In contrast, Einstein's insistence on determinism reflected his broader philosophical commitment to a rational, orderly universe. To Einstein, the idea that nature could be governed by chance or randomness was incompatible with his understanding of the world, which was rooted in his work on relativity. As the debates continued, both men maintained their positions, with neither fully convincing the other. However, the exchange between Bohr and Einstein was instrumental in shaping the future direction of quantum mechanics. While Einstein's skepticism of quantum mechanics would remain a central theme in his later work, it was Bohr's views that ultimately prevailed. Over time, experiments would demonstrate that quantum mechanics, with its probabilistic predictions and wave-particle duality, accurately described the behavior of particles at the atomic and subatomic levels. Einstein's vision of a deterministic universe, while compelling, was unable to account for the strange, counterintuitive phenomena observed in the quantum world. In many ways, the Bohr-Einstein debates represented the broader tension between the classical worldview and the emerging quantum paradigm. Einstein's theories of relativity had shown that the universe was far more complex and strange than had been previously imagined, yet he remained steadfast in his belief that the world could still be understood through deterministic laws. Bohr, conversely, embraced the strangeness of the quantum world, seeing in its unpredictability a reflection of the true nature of reality. The debates between Bohr and Einstein were not just intellectual exercises, they were part of a broader philosophical struggle over how we should understand the universe. Bohr's victory in these debates did not mean the end of Einstein's influence on physics. His contributions to the theory of relativity and his insights into the nature of light and energy continue to shape modern physics today. However, the debates between Bohr and Einstein served to highlight the profound philosophical implications of quantum mechanics and the nature of scientific inquiry itself. The struggle to understand the quantum world is not just a technical challenge, but a deep philosophical question that continues to inspire scientists, philosophers, and thinkers alike. Their debates are a testament to the importance of intellectual humility and the willingness to question even the most fundamental assumptions about the nature of reality. In the end, the Bohr-Einstein debates did not just change our understanding of quantum mechanics, they changed the way we think about science, observation, and the nature of truth itself. Niels Bohr's legacy extends far beyond his contributions to atomic theory and quantum mechanics. His influence reshaped modern physics, not only through his groundbreaking theoretical work, but also through his role as a mentor, educator, and a driving force in the development of new ideas in nuclear physics. His visionary understanding of quantum mechanics, his establishment of the Copenhagen interpretation, and his focus on the role of the observer in measurement transformed the way scientists thought about the subatomic world. However, his contributions to the development of nuclear physics, his philosophical reflections, and his leadership in establishing the Institute for Theoretical Physics in Copenhagen demonstrate the breadth of his impact on the scientific community and beyond. One of the most significant aspects of Bohr's legacy is his role in the development of nuclear physics. In the late 1930s, Bohr's work on the structure of the atom laid the foundation for the development of nuclear fission, the process by which atoms of heavy elements like uranium are split to release vast amounts of energy. This discovery would later play a pivotal role in the development of nuclear energy and the creation of nuclear weapons. The discovery of nuclear fission in 1938 by Otto Hahn and Fritz Strassmann was followed by a theoretical explanation from Lise Meitner and Otto Frisch, who recognized the process as nuclear fission. Bohr's insight into the structure of the atom and his subsequent work on nuclear reactions greatly contributed to the understanding of fission and its potential applications. Bohr's involvement in nuclear physics became even more crucial during World War II. After fleeing Denmark to escape the Nazi occupation, Bohr traveled to the United States, where he contributed to the Manhattan Project, the U.S. effort to develop an atomic bomb. While Bohr was concerned about the potential for nuclear weapons to be used destructively, his involvement in the project was essential in providing scientific guidance on nuclear reactions and chain reactions. However, Bohr was not merely a passive participant in the Manhattan Project. He was deeply concerned about the long-term consequences of nuclear weapons and advocated for international control over atomic energy. His efforts to encourage global cooperation on nuclear research were later reflected in his call for the peaceful use of atomic energy and his support for the creation of international institutions to oversee nuclear weapons and technology. Bohr's contribution to nuclear physics was not just about technical knowledge. He also thought deeply about the ethical and political implications of atomic energy. In the years following World War II, Bohr became an advocate for the peaceful use of nuclear technology and promoted the idea of international collaboration in nuclear research. He argued that the power of nuclear energy could be used for the benefit of humanity, but only if it was regulated and controlled in a manner that prevented its misuse for military purposes. Bohr's belief in international cooperation and his efforts to promote peace through science were rooted in his broader philosophical views on the role of science in society. He saw science not just as a pursuit of knowledge, but as a force for good that could bring people together, transcending national boundaries and political differences. Another key aspect of Bohr's legacy was his leadership in the scientific community. In 1921, Bohr founded the Institute for Theoretical Physics in Copenhagen, which became one of the most important centers for research in quantum mechanics and nuclear physics. The institute attracted many of the brightest minds of the time, including Werner Heisenberg, Wolfgang Pauli, and Max Born, who would go on to make groundbreaking contributions to the field. Bohr's ability to create a collaborative environment where scientists from around the world could exchange ideas and work together on cutting-edge research played a critical role in the development of modern physics. The Institute not only produced some of the most important discoveries in the history of science, but also served as a hub for the global scientific community. Under Bohr's guidance, the Institute became a melting pot of scientific innovation. He encouraged his colleagues to think outside the box, to embrace uncertainty, and to question the very foundations of physics. Bohr's own approach to science was characterized by a deep curiosity and a willingness to accept the unknown. This intellectual openness helped to foster an environment where radical new ideas could flourish, and it became a model for scientific institutions around the world. Many of the world's leading physicists passed through the Institute for Theoretical Physics, making it one of the most influential research centers of the 20th century. Bohr's contributions to science were also shaped by his philosophical reflections on the nature of reality. He was deeply concerned with the implications of quantum mechanics for our understanding of the world. The principles of uncertainty and complementarity, which he championed, forced scientists to reconsider the very nature of physical reality. Bohr's views on the relationship between observation and reality challenged the classical notion that the universe existed independently of human perception. He argued that the act of measurement was not a passive process, but an active one that played a role in defining the properties of a quantum system. This view marked a departure from classical physics, which held that objects had definite properties regardless of observation. Bohr's commitment to the idea of complementarity was rooted in his belief that different experimental perspectives could reveal different aspects of reality. He argued that no single description of a quantum system could fully capture its nature. Instead, complementary experiments, which revealed different facets of a system, were necessary to obtain a complete understanding. This view was central to the Copenhagen interpretation of quantum mechanics, which Bohr helped to establish. The Copenhagen interpretation remains one of the most widely accepted explanations of quantum mechanics, although it has also sparked debate and controversy over the years. Nevertheless, Bohr's contributions to the philosophy of science have had a lasting impact on how we think about the relationship between the observer and the observed and the limits of human knowledge. Beyond his technical and philosophical contributions, Bohr's impact on the scientific community can also be seen in his personal qualities. He was known for his humility and his willingness to listen to others, regardless of their status or reputation. Bohr's approach to science was always collaborative, and he believed that the best ideas often came from the exchange of ideas between individuals with different perspectives. He was a mentor to many young physicists, and his ability to inspire and guide them was a testament to his leadership and vision. Bohr's legacy as a teacher and mentor has been felt throughout the scientific community, and his influence continues to shape the way scientists approach their work. Niels Bohr's contributions to physics were not just theoretical, they were also practical. His work on nuclear reactions, his role in the Manhattan Project, and his efforts to promote international cooperation in nuclear research have had a lasting impact on the world. Bohr's vision for the peaceful use of atomic energy, his commitment to scientific collaboration, and his philosophical reflections on the nature of reality have left an indelible mark on modern science. His legacy continues to inspire scientists, philosophers, and thinkers to explore the mysteries of the quantum world and to seek new ways to apply scientific knowledge for the benefit of humanity. In conclusion, Niels Bohr's legacy is a testament to his intellectual brilliance, his commitment to collaboration, and his profound philosophical insights into the nature of reality. His contributions to quantum mechanics, nuclear physics, and the philosophy of science have shaped the course of modern physics and continue to influence our understanding of the universe. Bohr's work was not just about discovering new scientific principles, it was about rethinking the very nature of science and its role in society. His legacy as a scientist, mentor, and philosopher has made him one of the most important figures in the history of science, and his ideas continue to resonate with scientists and thinkers today. Niels Bohr's impact on the development of quantum mechanics, particularly his formulation of the complementarity principle and his foundational role in the Copenhagen interpretation, was central to transforming how we understand the microscopic world. Bohr's early work on atomic structure, particularly his model of the atom in 1913, was a cornerstone of quantum theory and paved the way for much of the 20th century's scientific discoveries. His influence was not limited to just theoretical physics. His work on the philosophical implications of quantum mechanics fundamentally changed our perception of reality. The concept of complementarity, one of Bohr's most important contributions, was a radical shift in how scientists thought about the behavior of subatomic particles. Complementarity proposed that objects, like light and matter, could display different properties depending on the experimental context, with contradictory observations being valid in their own right. In other words, phenomena like light could behave both as a wave and a particle, but these two descriptions could not be observed simultaneously. The theory was a direct challenge to classical physics, where the properties of objects were thought to exist independently of how they were observed. This was a pivotal moment in the history of science because it suggested that the act of measurement itself could alter the state of what was being measured, fundamentally questioning the notion of objective reality. In practical terms, Bohr's complementarity principle offered a way to reconcile the seemingly contradictory results in the growing body of experimental evidence surrounding atomic behavior. For example, in the famous double-slit experiment, light could produce both interference patterns, suggesting it was a wave, and particle-like impacts on a detector screen, suggesting it was a particle. Bohr argued that both descriptions were valid, depending on whether the experiment was designed to observe the wave-like or particle-like behavior. However, one could not simultaneously observe both, because the measurement process itself would collapse the system into one state or the other, thus eliminating the other possibility. Complementarity not only solved practical issues in atomic physics, but also raised profound philosophical questions about the nature of knowledge, observation, and reality. The question of what constitutes reality, if the act of observation changes the observed system, was one of the most significant philosophical dilemmas that emerged from quantum mechanics. Before Bohr, the classical assumption was that the world existed independently of human perception and that science could reveal the objective truth about the universe. However, Bohr's interpretation challenged that assumption. According to Bohr, knowledge of the universe was not purely objective and could not be fully separated from the process of observation. The concept of complementarity thus raised significant epistemological questions. What is real if observation itself can alter the outcome? Bohr's views had far-reaching implications not only for physics but also for philosophy, as they forced a re-evaluation of how we understand the relationship between subject and object, observer and observed. As Bohr advanced his theories on complementarity, his thoughts on the Copenhagen interpretation of quantum mechanics became central to his legacy. Developed during the 1920 seconds, the Copenhagen interpretation argued that quantum systems do not have definite properties until they are measured. Prior to measurement, particles exist in a state of probability, described by a wave function that represents the likelihood of finding a particle in a particular state. The wave function itself is a mathematical abstraction, and the reality of the particle's location or momentum is not determined until a measurement is made. This probabilistic view of nature stood in stark contrast to classical mechanics, which was deterministic and assumed that the properties of particles could be known with certainty at all times. The Copenhagen interpretation rejected the idea that there is an objective reality independent of the observer. Instead, it proposed that physical properties, such as position or momentum, do not exist in a well-defined state until they are measured. This notion that measurement affects the state of the system was a profound shift from the Newtonian conception of the universe, where objects followed deterministic paths and existed in fixed, well-defined states. The implications of this idea were staggering. If the properties of particles are indeterminate until observed, how can we understand the nature of reality itself? Bohr's position was that reality, as described by quantum mechanics, was inherently probabilistic, and that our understanding of it must include the role of the observer. One of the key debates that arose from the Copenhagen interpretation was Bohr's famous exchanges with Albert Einstein. Einstein was deeply uncomfortable with the probabilistic nature of quantum mechanics and famously quipped, "God does not play dice with the universe." For Einstein, this probabilistic view was a sign that the theory was incomplete, and that there must be hidden variables, unknown elements of nature that would explain the behavior of quantum particles in a deterministic way. He believed that quantum mechanics, while successful in predicting outcomes, did not provide a complete understanding of the underlying reality. Bohr, on the other hand, embraced the indeterminacy, arguing that it was not due to a lack of knowledge, but was an intrinsic property of nature. Their debates about the completeness of quantum theory were not only a contest of scientific ideas, but also a clash of philosophical perspectives on the nature of reality, determinism, and knowledge. In practical terms, the Copenhagen interpretation, as developed by Bohr and his colleagues, had profound consequences for the field of quantum mechanics and set the stage for future experiments and advancements. It was the foundation for much of the theoretical work that followed and provided a framework for understanding the behavior of subatomic particles in ways that were previously unimaginable. For instance, Bohr's work influenced the development of the uncertainty principle, formulated by Werner Heisenberg, which articulated that there is a fundamental limit to how precisely we can measure certain pairs of properties of particles, such as position and momentum. This principle, along with the Copenhagen interpretation, highlighted the inherently probabilistic and indeterminate nature of the quantum world, which directly contradicted the deterministic framework of classical physics. Bohr's vision of quantum mechanics also had a significant impact on the development of atomic theory and nuclear physics. The Bohr model of the atom, which suggested that electrons orbited the nucleus in discrete energy levels, provided the foundation for understanding atomic structure. Later work, such as the development of quantum field theory, built on Bohr's work, but it was his earlier contributions that provided the crucial stepping stones for these later breakthroughs. Furthermore, Bohr's participation in the Manhattan Project during World War II, as well as his advocacy for the peaceful use of nuclear energy, was a direct consequence of his deep understanding of atomic physics and its potential applications. Niels Bohr's legacy as a physicist is also closely tied to his ability to foster collaboration and mentorship in the scientific community. Bohr's Institute for Theoretical Physics in Copenhagen, established in 1921, became a hub for some of the most prominent physicists of the 20th century. It was here that physicists like Werner Heisenberg, Wolfgang Pauli, and Max Born worked alongside Bohr, developing the foundations of quantum mechanics. The Institute was not just a place for scientific work. It was a community where ideas could be exchanged freely and where new theories could be developed. Bohr's leadership was instrumental in creating an environment where scientific discovery could flourish, and his role as a mentor to many of the most prominent physicists of the time cemented his legacy as one of the most influential figures in the history of science. In conclusion, Niels Bohr's contributions to the development of quantum mechanics, particularly through his theory of complementarity and the Copenhagen interpretation, changed the way we understand the universe. His work shifted the focus of physics from deterministic laws to probabilistic outcomes, fundamentally altering our view of reality. Bohr's influence extended beyond theoretical physics into the realm of philosophy, as his ideas challenged the concept of an objective, independent reality and introduced the role of the observer into the equation. His leadership in the scientific community and his contributions to the development of atomic and nuclear physics left a lasting impact on modern science. The Bohr-Einstein debates, while never fully resolved, highlighted the philosophical and scientific tensions that continue to shape quantum mechanics today. Niels Bohr's legacy is not just in his scientific discoveries, but in his profound influence on how we think about the world, our place in it, and the nature of knowledge itself. Niels Bohr's contributions to the world of physics and quantum mechanics are monumental, and his legacy is defined not only by his theoretical breakthroughs but also by his leadership in the scientific community, his profound philosophical reflections on the nature of science, and his ability to influence generations of physicists. In the second part of Bohr's legacy, we delve deeper into the broader implications of his work, his impact on the development of nuclear physics, and his role as a mentor and a leader in scientific thought. Bohr's approach to quantum mechanics, his views on the relationship between science and philosophy, and his influence on the future directions of research continue to shape the landscape of modern physics. One of the most important aspects of Bohr's later life and legacy was his involvement in nuclear physics, which began as a direct consequence of his work on atomic structure. After Bohr developed his model of the atom in 1913, he contributed significantly to the development of nuclear physics, particularly during the early stages of the 20th century, when the understanding of the atom was rapidly evolving. His insights into the atomic nucleus and the behavior of subatomic particles helped to pave the way for the discovery of nuclear fission and the eventual development of nuclear energy. In the late 1930s, Bohr's work on the atom contributed directly to the understanding of nuclear reactions. The discovery of nuclear fission in 1938 by Otto Hahn and Fritz Strassmann, which showed that uranium atoms could be split to release large amounts of energy, was a turning point in nuclear physics. While this discovery was groundbreaking in itself, it was Bohr who provided the theoretical explanation for the phenomenon, demonstrating that the energy released during fission could be explained by the splitting of the uranium nucleus into two smaller nuclei. This work on nuclear fission laid the foundation for the development of both nuclear energy and nuclear weapons. As World War II intensified, Bohr's scientific expertise became crucial in the development of the atomic bomb. Bohr was forced to flee Denmark after the Nazi occupation in 1943, and he made his way to the United States, where he became involved in the Manhattan Project, the U.S. effort to develop atomic weapons. Though Bohr's primary focus was on the scientific aspects of nuclear reactions, he was deeply concerned about the potential use of nuclear technology for military purposes. Bohr's moral and ethical concerns about nuclear weapons were voiced in his famous correspondence with U.S. President Franklin D. Roosevelt, in which he called for international cooperation in the peaceful use of nuclear energy and warned against the dangers of nuclear weapons in the wrong hands. Bohr's involvement in the Manhattan Project was marked by his desire to ensure that atomic energy would not be used destructively. Although he contributed valuable scientific knowledge to the project, he did not directly participate in the development of the atomic bomb. Instead, Bohr was concerned with the long-term consequences of nuclear weapons and advocated for international oversight and regulation of atomic energy. Bohr's moral stance on nuclear weapons was based on his belief in the importance of scientific progress being balanced with ethical responsibility. He believed that nuclear technology had the potential to improve the world, but only if it was regulated and used for peaceful purposes. In addition to his work on nuclear physics, Bohr's legacy also lies in his contributions to the broader scientific community. In 1921, Bohr established the Institute for Theoretical Physics in Copenhagen, which became one of the most important centers for research in quantum mechanics and nuclear physics. The institute attracted many of the brightest minds in physics, including Werner Heisenberg, Max Born, and Wolfgang Pauli, all of whom made significant contributions to the field under Bohr's guidance. The institute became a vibrant center of collaboration and innovation, where ideas could be exchanged freely and new theories could be developed. Bohr's ability to foster such an environment of scientific collaboration was a key part of his leadership style and cemented his role as a central figure in the development of modern physics. The Institute for Theoretical Physics played a pivotal role in advancing the understanding of quantum mechanics, with Bohr serving as a mentor to many young physicists. He was known for his humility and willingness to engage with others, regardless of their status. Bohr's leadership was characterized by his ability to inspire and encourage those around him, and his intellectual generosity helped to create a scientific community where new ideas could flourish. Bohr's mentorship was instrumental in the success of many prominent physicists, and his influence extended far beyond his own research. The Institute, and Bohr's leadership within it, was integral to the development of quantum mechanics and the overall progress of 20th century physics. As a mentor, Bohr also shaped the future direction of quantum mechanics. While many of his colleagues were focused on refining the technical aspects of the theory, Bohr's unique insight into the philosophical implications of quantum mechanics set him apart. Bohr believed that quantum theory required not only a new understanding of physical systems, but also a re-evaluation of the nature of scientific knowledge. In his work on complementarity and the Copenhagen interpretation, Bohr argued that the act of measurement was not merely a passive observation of nature, but an active process that shaped the reality being measured. This radical view of the observer's role in the quantum world challenged traditional ideas about the relationship between the observer and the observed. It required scientists to reconsider the very nature of reality itself and the limits of human knowledge. Bohr's work also had far-reaching philosophical implications. His idea that reality was fundamentally probabilistic and that the observer played a role in shaping the outcome of a measurement was a profound challenge to the classical notion of an objective reality. Before Bohr, scientists believed that the universe existed independently of human perception and that science could uncover the objective truth about the world. Bohr, however, argued that the quantum world did not conform to these classical assumptions. In Bohr's view, the properties of quantum systems were not predetermined or definite, but depended on the type of measurement made and the way in which the system was observed. This view had deep philosophical implications, particularly with regard to the concept of objective reality. Bohr's thoughts on the relationship between science and philosophy influenced not only the development of quantum mechanics, but also the broader philosophical discourse on the nature of knowledge and truth. His work on complementarity was not just a technical contribution to physics, but a reflection on the limitations of human understanding. Bohr recognized that science could only provide partial knowledge of the world and that some aspects of reality could never be fully understood or explained. This recognition of the limits of science was one of Bohr's most profound philosophical insights and is reflected in his famous quote, "Anyone who is not shocked by quantum theory has not understood it." Bohr's legacy also extends beyond physics and philosophy to the field of education. His commitment to nurturing the next generation of physicists and encouraging collaboration across national and disciplinary boundaries helped to shape the scientific community of the 20th century. Bohr's Institute in Copenhagen, as well as his personal mentorship, created an intellectual environment that allowed for the rapid development of quantum theory and its applications. The scientific advancements of the mid-20th century were made possible in large part because of Bohr's leadership, his encouragement of young scientists, and his ability to bring together diverse minds to work toward a common goal. In conclusion, Niels Bohr's legacy is one of profound influence, not only in the field of quantum mechanics but also in the development of nuclear physics, the philosophical implications of science, and the future direction of scientific inquiry. His contributions to atomic theory and quantum mechanics laid the foundation for much of modern physics, while his leadership and mentorship helped to shape the next generation of scientists. Bohr's ideas on complementarity and the Copenhagen interpretation continue to shape our understanding of the quantum world, and his work has had a lasting impact on both the technical and philosophical aspects of science. Through his intellectual contributions, his ethical stance on nuclear energy, and his dedication to scientific collaboration, Bohr has left a legacy that continues to inspire and guide physicists to this day. Niels Bohr's impact on the development of quantum mechanics and atomic theory cannot be overstated. His contributions, particularly his model of the atom and his development of the complementarity principle, revolutionized our understanding of the subatomic world. At the heart of Bohr's contributions was his groundbreaking model of the atom, introduced in 1913. This model replaced the classical view of the atom as a miniature solar system where electrons orbited the nucleus in continuous paths. Instead, Bohr proposed that electrons exist in discrete orbits with specific energy levels, and they could absorb or emit energy only when transitioning between these levels. This concept of quantized electron orbits was revolutionary and helped explain why atoms were stable and how they emitted specific light frequencies. Bohr's model not only explained the stability of atoms, but also offered a solution to the mystery of atomic spectra. Classical physics had been unable to explain the discrete lines in the spectrum of hydrogen, but Bohr's model did so with remarkable accuracy. His theory of quantization, though initially controversial, was ultimately confirmed by experimental evidence, marking a major step forward in atomic physics. This breakthrough laid the foundation for the development of quantum mechanics, which would later describe the behavior of particles on the smallest scales, far beyond the capacity of classical physics. The concept of complementarity, one of Bohr's key contributions, extended his revolutionary ideas about the atom to a broader philosophical understanding of quantum mechanics. Complementarity suggested that particles like light could exhibit contradictory properties depending on the experimental setup. For instance, light could behave as both a wave and a particle, depending on the type of experiment performed. This principle posed a direct challenge to classical ideas about the nature of reality, where objects were believed to have definite properties, regardless of observation. Complementarity introduced a new way of thinking about scientific observations. Rather than viewing the properties of particles as fixed and objective, Bohr argued that they could only be understood in relation to the context of the experiment and the type of measurement being made. This principle raised profound questions about the nature of reality itself. If the properties of particles depended on observation, how could scientists be sure they were uncovering objective truths about the universe? Bohr's answer was that reality at the quantum level was inherently probabilistic, and the role of the observer was integral to the measurement process. This view marked a break from classical notions of objective reality and set the stage for the Copenhagen interpretation of quantum mechanics. According to the Copenhagen interpretation, particles do not have definite properties until they are observed, and the act of observation itself can influence the outcome. This idea went against classical physics, which held that objects had definite properties whether or not they were observed. Another critical contribution of Bohr's work was his role in the development of the Copenhagen interpretation of quantum mechanics. This interpretation, developed in collaboration with other physicists like Werner Heisenberg, argued that the quantum world operates on principles of probability, not certainty. In the classical view, if we knew the initial conditions of a system, we could predict its future behavior with complete accuracy. However, quantum mechanics suggested that the behavior of particles could only be predicted probabilistically, not deterministically. This shift in perspective was a profound change in the way scientists viewed the universe. Rather than seeing the universe as a clockwork machine governed by fixed laws, Bohr's interpretation suggested that nature itself was governed by uncertainties that could not be resolved with perfect precision. Bohr's philosophical stance on quantum mechanics was one of acceptance of this uncertainty. He recognized that, at the subatomic level, our traditional notions of cause and effect and our ability to predict outcomes with certainty simply did not apply. This was encapsulated in his famous statement, "Anyone who is not shocked by quantum theory has not understood it." Bohr's interpretation emphasized that the probabilistic nature of quantum mechanics was not a sign of incomplete knowledge, but a reflection of the fundamental properties of the quantum world. His acceptance of indeterminacy and his willingness to embrace the strange and counterintuitive nature of quantum theory made him a key figure in the development of modern physics. Niels Bohr's work in the early 20th century redefined the structure of the atom and laid the groundwork for quantum mechanics. His most pivotal achievement was his development of the Bohr model of the atom in 1913, which departed from classical physics and introduced the idea that electrons exist in discrete energy levels or orbits. Before Bohr, the atom was viewed as a miniature solar system where electrons orbited the nucleus in continuous paths. Similar to planets orbiting the Sun, Bohr's insight was to propose that electrons could only occupy specific orbits, and they would absorb or emit energy only when jumping from one orbit to another. This model explained atomic stability, as classical physics had failed to address why electrons did not spiral into the nucleus. Bohr's model not only explained why atoms emitted light in discrete spectral lines but also provided an explanation for why atoms are stable, something classical physics could not achieve. Though initially met with resistance, experimental evidence soon confirmed Bohr's predictions, marking the beginning of a new era in atomic physics. Bohr's contributions extended beyond just atomic structure. His complementarity principle, which he introduced in the 1920 seconds, revolutionized the way scientists understood the nature of quantum mechanics. Complementarity suggested that objects could exhibit contradictory properties depending on how they were observed. For example, light could behave both as a wave and as a particle, depending on whether it was observed through experiments designed to detect its wave-like or particle-like behavior. This principle was a direct challenge to classical physics, which believed in the objective, independent existence of properties. According to Bohr, the properties of quantum systems were not absolute but depended on the experimental context. The complementarity principle was not just a technical insight, but also a profound philosophical shift in how reality itself was perceived. It questioned whether we could ever fully comprehend nature at its most fundamental level, as the act of observation seemed to alter what was being observed. As the central figure in the Copenhagen interpretation of quantum mechanics, Bohr shaped how physicists thought about the nature of particles and waves. The Copenhagen interpretation, developed alongside physicists like Werner Heisenberg, argued that quantum systems exist in a state of probability rather than certainty until they are measured. In the classical view, if we knew the initial conditions of a system, we could predict its future behavior with certainty. But quantum mechanics suggested that particles could only be described in terms of probabilities, and their properties were indeterminate until they were observed. The Copenhagen interpretation fundamentally changed the way scientists thought about the universe, replacing deterministic classical mechanics with a probabilistic framework. Bohr's assertion that the act of measurement influenced the state of a system was a dramatic departure from the classical notion that an object's properties existed independently of observation. The Copenhagen interpretation remains one of the most widely accepted interpretations of quantum mechanics today, though it remains controversial for its philosophical implications. Beyond his theoretical contributions, Bohr also had a significant impact on the global scientific community through his role as a mentor and educator. In 1921, he founded the Institute for Theoretical Physics in Copenhagen, which became a central hub for research in quantum mechanics and nuclear physics. The institute attracted some of the brightest minds of the 20th century, including physicists like Werner Heisenberg, Wolfgang Pauli, and Max Born. The environment at the institute encouraged collaboration and intellectual exchange, and Bohr played a crucial role in fostering this cooperative atmosphere. His ability to bring together scientists from different backgrounds to work on shared problems created a fertile ground for new ideas and breakthroughs in the field of quantum mechanics. Bohr's role as a mentor also helped shape the next generation of physicists, many of whom would go on to make their own groundbreaking contributions to science. Bohr's influence was not limited to atomic physics and quantum mechanics. He played a key role in the development of nuclear physics and, later, in the political and ethical discussions surrounding nuclear weapons. After fleeing Denmark during the Nazi occupation in 1943, Bohr moved to the United States, where he became involved in the Manhattan Project, the U.S. initiative to develop the atomic bomb. Though Bohr did not directly participate in the development of the bomb, his work on nuclear reactions contributed to the understanding of fission, the process behind the explosion of nuclear weapons. However, Bohr was deeply concerned about the destructive potential of nuclear technology. He advocated for international cooperation and control over atomic energy, and became a leading voice in calling for the peaceful use of nuclear technology after World War II. His efforts to raise awareness about the dangers of nuclear weapons and promote global cooperation in their regulation have had a lasting impact on the development of nuclear policy in the post-war world. Bohr's moral stance on the use of nuclear energy reflected his broader philosophical commitment to ensuring that scientific progress was used for the betterment of humanity, not for destruction. In conclusion, Niels Bohr's contributions to science, philosophy, and global politics shaped the course of the 20th century. His work on atomic theory, quantum mechanics, and the complementarity principle transformed the way we understand the atomic world and the very nature of reality. Through his leadership at the Institute for Theoretical Physics, his mentorship of future scientific leaders, and his ethical stance on the use of nuclear energy, Bohr's influence extended far beyond the laboratory. His ideas have had lasting implications not only for the field of physics, but also for the philosophical and political debates that continue to shape the modern world. Niels Bohr's profound impact on the development of modern physics is most notably embodied in his model of the atom and his contributions to the foundation of quantum mechanics. His work in atomic theory challenged the existing paradigms of classical physics and opened new avenues for understanding the behavior of matter at the microscopic level. One of his most groundbreaking achievements was the introduction of the Bohr model of the atom in 1913, which proposed that electrons orbit the atomic nucleus in discrete energy levels, known as shells. This was a significant departure from the classical view that electrons moved in continuous orbits. The Bohr model successfully explained the stability of atoms and the emission spectra of hydrogen. Before Bohr, it was unclear why atoms did not collapse under the electromagnetic force of the electrons, which should have caused them to spiral into the nucleus. Bohr's model resolved this by introducing quantization, suggesting that electrons could only occupy certain allowed orbits, each associated with a specific energy level. When electrons moved between these orbits, they absorbed or emitted energy in discrete quantities, a concept that became fundamental to the development of quantum theory. Along with the Bohr model, Niels Bohr's contributions to the Copenhagen interpretation of quantum mechanics were instrumental in shaping our understanding of the quantum world. The Copenhagen interpretation, developed with his colleagues in the 1920 seconds, asserted that quantum systems exist in a state of probability until measured. Before observation, particles such as electrons or photons are described by a wave function which encodes all possible outcomes of a measurement. Only upon measurement does the system collapse into one definite state. This concept of wave-particle duality, in which particles can exhibit properties of both waves and particles, was an essential element of the Copenhagen interpretation. The idea that the observer plays a central role in determining the outcome of a quantum measurement was a radical departure from classical physics, where it was assumed that the properties of objects existed independently of observation. This notion opened the door to a new understanding of reality, where observation and measurement were integral to the nature of quantum systems, leading to a paradigm shift in both physics and philosophy. Niels Bohr's philosophical approach to quantum mechanics was rooted in his concept of complementarity, which proposed that seemingly contradictory aspects of reality could coexist, depending on the experimental context. For example, in the famous double-slit experiment, light can behave as both a wave and a particle, depending on whether the experiment is set up to observe its wave-like or particle-like properties. Bohr suggested that both descriptions of light were valid, but they were complementary. They provided different perspectives of the same underlying reality, but could not be observed simultaneously. This idea of complementarity was not only crucial for understanding quantum mechanics, but also had far-reaching implications for how we think about the nature of reality itself. The complementarity principle emphasized that our understanding of the universe is shaped by the limits of our measurement tools and the context in which we conduct experiments. Bohr's willingness to embrace this paradoxical nature of quantum reality marked him as one of the most innovative and open-minded thinkers in the history of science. The Bohr-Einstein debates, which took place in the 1,920 seconds and 1,930 seconds, represent one of the most famous intellectual exchanges in the history of science. These debates centered around the question of whether quantum mechanics was a complete theory or whether there were hidden variables that could explain its probabilistic nature. Albert Einstein famously objected to the probabilistic interpretation of quantum mechanics, stating that God does not play dice with the universe. Einstein believed that quantum mechanics was incomplete and that a deeper, deterministic theory would eventually emerge to explain the randomness observed in quantum systems. Bohr, however, defended the probabilistic nature of quantum mechanics, arguing that this uncertainty was a fundamental feature of nature and could not be eliminated by a hidden variable theory. Their debates pushed the boundaries of scientific understanding and helped to solidify the foundations of quantum mechanics, despite the philosophical and conceptual challenges they posed. The discussions between Bohr and Einstein, particularly over the role of determinism and uncertainty in the quantum world, continue to shape modern interpretations of quantum theory. In addition to his contributions to the theoretical foundations of quantum mechanics, Bohr played a significant role in the development of nuclear physics. After the discovery of nuclear fission in the late 1930 seconds, Bohr's work on the structure of the atom and nuclear reactions became increasingly important. His understanding of atomic nuclei and their behavior under various conditions helped to explain the processes of nuclear fission and the release of energy from splitting heavy atoms. In the early 1940 seconds, as World War II raged on, Bohr's expertise became crucial in the development of nuclear weapons. He fled Denmark during the Nazi occupation and went to the United States, where he became involved in the Manhattan Project, the U.S. effort to develop an atomic bomb. Bohr's scientific knowledge and his insights into nuclear reactions were instrumental in the development of nuclear technology. However, Bohr was deeply concerned about the consequences of nuclear weapons and advocated for international cooperation in controlling nuclear energy. His moral and ethical stance on nuclear weapons led him to campaign for the peaceful use of atomic energy after the war. Bohr's leadership and mentorship had a lasting impact on the scientific community. In 1921, he founded the Institute for Theoretical Physics in Copenhagen, which became one of the world's leading centers for research in quantum mechanics and nuclear physics. The institute attracted many of the brightest physicists of the 20th century, including Werner Heisenberg, Wolfgang Pauli, and Max Born. Bohr's influence as a mentor extended far beyond his own research. He played a pivotal role in shaping the careers of many future Nobel laureates. The Institute was a center of innovation and collaboration, where young physicists could explore new ideas and work alongside some of the greatest minds in the field. Bohr's open-mindedness and his commitment to fostering scientific dialogue and cooperation helped to create an intellectual environment that accelerated the development of quantum theory. His leadership also established a model for scientific collaboration, which remains important in modern research. Bohr's influence on the philosophy of science and the interpretation of quantum mechanics also extended beyond the realm of physics. His ideas about the relationship between observation and reality, as well as his concept of complementarity, had profound implications for our understanding of the limits of scientific knowledge. Bohr's emphasis on the uncertainty and probabilistic nature of quantum mechanics challenged the classical idea of a fully deterministic universe. He argued that the universe was inherently indeterminate at the quantum level and that this uncertainty was a fundamental aspect of reality. Bohr's philosophy of science called into question the very nature of knowledge and the ability of science to provide definitive answers about the universe. His ideas continue to shape not only the field of physics, but also broader philosophical discussions about the nature of reality, knowledge, and the limits of human understanding. In conclusion, Niels Bohr's contributions to quantum mechanics, nuclear physics, and the philosophy of science were revolutionary and continue to influence the direction of scientific thought today. His Bohr model of the atom, his development of the complementarity principle, and his role in the Copenhagen interpretation of quantum mechanics transformed our understanding of the subatomic world. Bohr's leadership in nuclear physics, his mentorship of future scientists, and his commitment to the ethical use of nuclear technology have had a lasting impact on the scientific community and the world at large. His philosophical reflections on the nature of reality and the limits of scientific knowledge have made him one of the most influential thinkers in modern history. Through his intellectual achievements and his moral and ethical leadership, Bohr has left an indelible mark on both science and philosophy. Niels Bohr's role in the development of quantum mechanics and atomic theory cannot be overstated. His most famous contribution, the Bohr model of the atom, introduced in 1913, was a revolutionary step in understanding the structure of the atom. Prior to Bohr, the atom was thought to resemble a miniature solar system, with electrons orbiting the nucleus like planets orbiting the sun. However, this classical view failed to explain why atoms emitted light in discrete spectral lines. Bohr proposed that electrons do not travel in continuous orbits, but instead exist in fixed energy levels. When an electron jumps between these levels, it absorbs or emits energy in discrete amounts, creating the observed spectral lines. This model successfully explained the stability of atoms and the nature of atomic spectra, which classical physics had failed to account for. Bohr's model laid the groundwork for the development of quantum theory and became a critical part of modern atomic physics. Bohr's work extended beyond atomic structure and into the realm of quantum mechanics, where he introduced his principle of complementarity. Complementarity proposed that objects such as light and matter could exhibit contradictory properties depending on the type of experiment performed. For instance, light could behave both as a wave and a particle, depending on whether the experiment was designed to detect its wave-like or particle-like nature. This idea of complementarity marked a departure from classical physics, where it was assumed that objects had definite, independent properties that could be observed at all times. Bohr's principle suggested that the nature of reality could not be fully understood in one single experiment, as the properties of quantum systems depend on how they are observed. This principle not only helped resolve contradictions in experimental results, but also had profound philosophical implications about the nature of reality itself. The Copenhagen interpretation of quantum mechanics, which Bohr helped develop in the 1920 seconds, was based on his philosophical views regarding complementarity. According to the Copenhagen interpretation, quantum systems do not have definite properties until they are measured. Before measurement, a system exists in a state of probability, described by a mathematical function known as the wave function. When a measurement is made, the wave function collapses to a definite state. This probabilistic nature of quantum mechanics was a fundamental break from classical determinism, where every event was seen as the result of preceding causes. Bohr's interpretation suggested that, at the quantum level, there is an inherent uncertainty, and the act of measurement itself determines the outcome. This idea challenged classical physics and was one of the most radical and transformative concepts in 20th century science. Bohr's work was not just about theoretical advancements, but also about pushing the boundaries of how science interacts with the broader philosophical and ethical questions of the time. His ideas on quantum mechanics and uncertainty had profound implications for our understanding of the universe. Before Bohr, science was based on the assumption that the universe could be fully understood through observation and reason. Bohr's principle of complementarity, however, suggested that we could not observe the world without altering it in the process. This led to deep philosophical questions about the nature of reality, knowledge, and the role of the observer in shaping our understanding of the world. Bohr argued that the relationship between the observer and the observed was central to understanding the quantum world, and this shifted the focus of scientific inquiry from objective reality to the act of measurement itself. Alongside his work in quantum mechanics, Bohr was a key figure in the development of nuclear physics. His understanding of atomic structure laid the foundation for later work on nuclear reactions, particularly nuclear fission. The discovery of nuclear fission in the late 1930s, when uranium atoms were found to split, releasing enormous amounts of energy, was a turning point in the history of physics. Bohr's theoretical insights helped explain the process of fission and contributed to the understanding of nuclear reactions. This knowledge would eventually play a central role in the development of nuclear power and nuclear weapons. During World War II, Bohr became involved in the Manhattan Project, which sought to develop the atomic bomb. Though he contributed scientific knowledge, he was also deeply concerned about the consequences of nuclear weapons and advocated for the peaceful use of atomic energy after the war. In addition to his scientific contributions, Bohr's leadership and mentorship shaped the next generation of physicists. In 1921, Bohr founded the Institute for Theoretical Physics in Copenhagen, which became a major center for research in quantum mechanics and nuclear physics. The institute attracted leading scientists from around the world, including Werner Heisenberg, Max Born, and Wolfgang Pauli. Bohr's influence as a mentor extended far beyond his own work, as he played a key role in the careers of many young physicists. The intellectual environment at the institute fostered collaboration and the exchange of ideas, and Bohr's guidance was crucial in the development of new theories in quantum mechanics. His leadership helped create a scientific community that was focused on solving the most challenging problems in physics, and his institute became one of the most important research centers of the 20th century. Bohr's work also had a significant impact on the ethical considerations surrounding scientific discoveries. As a central figure in the development of nuclear technology, Bohr was deeply concerned with the potential for nuclear weapons to be used destructively. After fleeing Nazi-occupied Denmark in 1943, Bohr traveled to the United States, where he became involved in the Manhattan Project. While Bohr contributed to the scientific development of atomic weapons, he also recognized the dangers they posed. His ethical stance on nuclear weapons was clear. He advocated for international cooperation in the peaceful use of atomic energy and argued for greater control over nuclear technology. Bohr's efforts to promote the peaceful use of nuclear energy and to prevent the misuse of nuclear weapons were pivotal in shaping the post-war scientific and political landscape. He believed that science must be used for the benefit of humanity, not for its destruction. In conclusion, Niels Bohr's contributions to atomic theory, quantum mechanics, and nuclear physics were groundbreaking and transformative. His Bohr model of the atom and his work on quantum mechanics laid the foundation for modern physics. His development of the complementarity principle and his role in the Copenhagen interpretation revolutionized our understanding of the quantum world, challenging classical ideas of reality and measurement. Bohr's leadership and mentorship shaped the future of physics, and his ethical stance on nuclear weapons and atomic energy left a lasting legacy. Through his scientific achievements, philosophical insights, and moral considerations, Bohr helped to shape the course of the 20th century and continues to influence the scientific community today.